The deflection sensitivity of an electrostatic deflection cathode ray tube is defined as the amount of spark deflection on the screen in mm per volt potential difference applied between the deflecting plates. It is expressed in mm per volt. Okay. The deflection sensitivity at the deflection the deflection sensitivity of the deflection sensitivity sensitivity the deflection sensitivity of an electrostatic deflection electrostatic deflection cathode ray tube is defined as the amount of spark deflection the amount of spark deflection on the screen in mm on the screen in mm per volt potential difference applied potential difference applied between the deflecting plates between the deflecting plates. It is expressed in mm per volt. It is expressed in mm per volt. Okay. The deflection sensitivity of an electrostatic deflection cathode ray tube defined as the amount of spark deflection on the screen in mm per volt potential difference applied between the deflecting plates. It is expressed in mm per volt. Okay. The DC or peak-to-peak AC voltage which must be applied across the deflection plates to produce a spark deflection of 1 mm on the screen is called deflection factor. Okay, deflection of 1 mm, deflection of 1 mm on the screen, deflection of 1 mm on the screen is called deflection factor. Okay, deflection factor. It is expressed in volt per mm. It is expressed in volts per mm. Okay. The deflection sensitivity is reciprocal of a deflection factor. The deflection sensitivity, thus deflection sensitivity, deflection sensitivity is reciprocal of deflection factor of deflection factor. Okay. To calculate the expression for electrostatic deflection sensitivity, let length of each deflection plate L. Length of each deflection plate, okay, L is length of each deflection plate. Each deflection plate, okay. L is length of each deflection plate, and D is distance between the plates. Distance between the plate. And capital D is distance between end of plates and screen. Distance between end of plates. Distance between end of plates and screen, okay. That is capital D, okay. That is capital D. If VA is the final accelerating anode voltage, if VA is the final accelerating anode voltage with the velocity of an electron and just entering the deflection plate, and small v the velocity of an electron just entering the deflection plates, then 1/2 mv square equal to E into VA, where E is the charge and m is the mass of an electron, okay. Where E is the charge and m is the mass of an electron, okay. Then V square equal to 2E/m into VA, okay. If BD is the voltage applied between the plates, then force acting on the electron towards the upper plate is given by force acting on the electron towards the upper plate is given by F equal to EVD by small d, okay. If A is the resulting accelerating of the electron, then A equal to E/m VD by d, where A equal to resulting acceleration. Acceleration of the electron, then equal to E/m VD by small d. Time taken by the electron to traverse through the length of deflection plates, then small t equal to L by V. Time taken by the electron to traverse through the length of deflection plates. Okay, hence upward velocity of the electron on emerging out of the deflection plates, then Vy equal to 0 plus 80. Okay, and upward velocity of the electron on emerging of the deflection plates. Okay, this is equation number 2. This is equation number 2 and this is equation number 1. Okay, the electron enters the deflecting system. The electron enters the deflection system at A and leaves at B. The path of the electron between A and B is curved. The path of the electron is A and B is curved. Okay. Okay. This is B. The hence upward velocity of the electron emerging out of the deflection plate. The electron enters the deflecting system at A and leaves at B. The path of the electron between A and B is curved. Vertically upward displacement. d1 during the time interval t is given by d1 equal to 0 plus half at square equal to 1 by 2 E by m Vd upon d into L square upon V square, that is EVD L square upon 2 mv square d. This is equation number third. Where d1 is the upward displacement. Upward displacement. Okay. After emerging from the plates, the electron beam moves in a straight line path, making an angle alpha with the original direction and meets the screen at y2. Okay. Meet the screen at y2. Okay. This is y1. This is y2, and this is d2. This is d1. Okay, d1, and this angle is alpha. Okay. Then after emerging from the plates, the electron beam remove in a straight path, making an angle alpha with the original direction and meets the screen at y2. Okay. Then now tan alpha equal to d2 upon capital D. Okay, d2 upon capital D. Okay, d2 upon capital D. 1 minute. d2 upon capital D. This is angle alpha. Okay, d2 upon capital D. d2 upon capital D. Okay. Then tan alpha equal to tan alpha equal to d2 upon capital D. That is Vy upon V. R d2 V2 equal to D Vy upon V, that is D upon V, E upon M, Vd upon D, L by V, that is L by V, that is EVD capital D, EVD capital D, L upon MV square D, that is equation number 4. This is equation number 4. Okay? That is equation number 4. 1 minute. This is equation number 4. And total deflection. Total deflection O Y2E OY1 plus Y1 Y2 equal to D1 plus D2. Okay? Equal to EVD L square, EVD L square upon 2 MD square D plus EVD LD upon MV square D, that is EVD L upon MV square D in bracket L by 2 plus D, that is equation number 5. If capital L is the distance of the screen from the screen of deflection plates, then if capital L is the distance of the screen from the center of the deflection plates, then capital L equal to L by 2, capital L equal to L by 2 plus D, L by 2 plus D. Okay? Substituting L by 2 plus D equal to capital L in relation 5, we have total deflection equal to EVD VD small l capital L upon MV square D. Okay? This is equation number 6. Substituting the value of V square, substituting the value of V square from first in 6, we get total deflection is EVD L capital L upon MD into M upon 2 VA into E equal to ILVD upon 2D VD. 2D VA. Hence deflection sensitivity S equal to deflection sensitivity S equal to total deflection upon voltage between the plates. Voltage between the plates. Okay. Then capital L upon 2D VD upon VD upon VA into 1 by VD into 1 by VD equal to IL upon 2D VA M per volt. Okay, this is 500 L capital L upon D VA mm per volt. Okay. From the relation 7, this is relation 7. Okay. From the relation 7, we find that electrostatic deflection sensitivity is directly proportional to the length of the deflection plates, and to the distance of the screen, screen from the center of plates. It is inversely proportional to the distance between the deflection plates and final anode voltage. Okay, total spark deflection. Total spark deflection sensitivity multiply applied voltage between the plates. Applied voltage between the plates. Deflection sensitivity into applied voltage between the plates. Okay. Thus we see that the deflection sensitivity can be increased by reducing the anode voltage. Thus we can see that the deflection sensitivity can be increased. By reducing the anode voltage. But this reduces the brightness of the spark. Okay? The disadvantage can be overcome by accelerating the beam after it has passed through the deflection system. This process is known as post acceleration and is brought about by using an extra electrode called the intensifier anode. Okay. This process is known as post acceleration and is brought about by using an extra electrode called the intensifier anode. Okay. Next, path described by electron in transverse magnetic field. Okay.